Hi, Algebra 2. In this lesson, we're going to be working with complex numbers and doing operations with them. This is one of probably the most abstract lessons of the whole year, but it's also a good one to challenge your brain. So dig in, and here we go. So the first thing we're looking at is this idea of the complex plane. So it's looking at the regular coordinate plane, but now our x-axis is where we are going to graph the real number part of a complex number, and the y-axis is where we graph the imaginary part of our complex number. So here we're going to practice graphing these numbers. So we first have 2 minus 3i. So the positive 2 is going to take us to right here on the real axis. And then the negative 3i, we're going to go down because it's negative or go down 3 units. So this is the point 2 minus 3i. Now for b, the negative 1 will take us on our real axis to the left one, and then 4i will take us up 4 units to right there. So this is the point negative 1 plus 4i, or the number negative 1 plus 4i. Okay, in c, the positive 4 will on the real axis will take us to right here, and then we go up 1. So this is the number 4 plus I right there. And the last one, d, is just negative I. So there is no real number part. So we're just going to go down 1 on our imaginary axis. So this is negative 1i right there. Next, we're going to look at the absolute value of a complex number. Remember that absolute value of a real number, so the absolute value you've worked with so far, is just its distance from 0 on a number line. In this case, that's the same as the real axis. So the absolute value of a complex number right here is its distance, like we just graphed, from the origin to that complex number. So right here, we're looking at the origin, and we're going to our complex number right there. So that distance is going to be the absolute value of our complex number. Now, finding that distance, we're going to go back to our Pythagorean theorem days, and we're going to make those triangles and use the Pythagorean theorem to get this distance. So here we're going to find the absolute value of a first, the absolute value of 3 plus 5i. So I've just sketched a graph. So here's 3 plus 5i. Remember, 3 on my real axis, up 5 on my imaginary. And I'm going to draw a triangle starting from the origin. This angle distance is the one we're looking for. And our vertical and our horizontal distances are what's going to help us get there. So this is a distance of 3, and our vertical distance here is 5. So the Pythagorean theorem is a squared plus b squared equals c squared. And our a here can be 3, our b can be 5, and we're looking for c. So now I'm going to simplify. 3 squared is 9, plus 5 squared is 25. That would be 34. Take the square root of both sides to get just c. And so I end up with c equals the square root of 34. And that's the distance of this right here, which it ends up being the absolute value of that complex number. In b, there's only a real part to this number. And so if I plot negative 13, it's going to be right there. Well, the distance from the origin to negative 13 is just 13. I don't really need to do any Pythagorean theorem there. Similarly with c, there is only an imaginary part, and so that number would be right there at negative 7i. Well, the distance from the origin to there is just 7, so that's the absolute value of negative 7i. So just keep remembering that absolute value is going to be the distance from the origin to your number. If it's an angle, you're going to have to use the Pythagorean theorem like we did in A. If it's just a straight line, you can just look at that distance. Next, we're going to add and subtract with our complex numbers. This is going to really feel just like combining like terms. So on this first one here, I could rewrite this without the parentheses because they're not really needed here. And then I can just look at my like terms. 4 and negative 6 would be negative 2. 2i and minus 7i would be negative 5i. So that's it. In the second one, I have 2i minus all of that in parentheses, 3 plus 5i. So I'm going to keep remembering that this is like -1 and use my distributive property to rewrite this. And then I just combine like terms. 2i and -5i would be -3i. And I have -3 out here. So -3 minus 3i. I could write it like this. It doesn't matter. Now we're going to do the addition by graphing. So this is a really interesting way to think of complex numbers. So 3 minus I is going to be right here. That's 3 minus I. And then plus 2 plus 3i. So I'm going to graph 2 plus 3i right here. And then I'm going to connect these points to the origin with a straight line. I'm going to use one color for 3 minus I. I'm going to use another color for 2 plus 3i. Now we're going to draw a parallelogram. And so I'm going to look at this side here. Notice that this line goes down 1 and over 3. So I'm going to go up to my other point here and go down 1 over 3, put a point there, and draw a line. So those two lines now are now parallel. They have the same slope. And I can connect this point over here. Now this point where those parallelogram lines meet is what I would end up with when I add them together. And so this is 5 plus 2i. So there's adding them together using a graph, creating parallelograms, which is a really interesting way to look at it. Now if you did look back up here and combine like terms, you'd have 3 and 2, which would be 5, -i and 3i, which would be your 2i. So it is the same thing. Now we're going to multiply. Before we start multiplying here with imaginary numbers, let's just remember that the square root of -1 is I, which means that I squared is -1. So just keep that in mind. This is going to be really important when we're multiplying. So we're going to use our distributive property just like we normally would. So over here we'd have -4i, and then here I'd have plus 8i squared. But I'm going to simplify this. I squared is -1. So I'm going to rewrite this as -4i plus 8 times -1 and keep simplifying. And it is more proper to do the term with I second. And so there it is. In this one, we just have to do more distributive property than we did in our other one. So this would be 12 minus 3i, and then plus 24i minus 6i squared. And so I'm going to simplify my like terms. And I remember that I squared is -1. And so I'm going to rewrite this as -1. And I just keep simplifying now. And combine like terms. And there we have it. So that is them multiplied together. It's really the same processes we've already used. You just have to remember that I squared is -1. Now we're going to divide with complex numbers. The key here is that you're going to end up multiplying by the conjugate of the denominator. So think back to when we were doing complex conjugates and we're like, what in the world are we ever going to use this for? Well, here's one use for it. So in this first one, I'm going to multiply by -5i. That is the complex conjugate of the denominator, but I don't want to change the value of this. So it's going to be -5i over -5i, which is just 1, right? So if we multiply by 1, we're not really changing the value. So now I'm going to multiply this out. This would be using the distributive property up here. So this would be -15i minus 50i squared. And then in the denominator, I'd have -25i squared. And the reason we're doing this is because we do not want to have an I in the denominator when we are simplifying our complex numbers here. So now I have a bunch of I squareds. Remember, I squared equals -1. So I'm going to simplify some more and put in that -1 for my i's, or I squared, excuse me. And I keep simplifying. I'm going to go over here so I have more room. I have all these negatives I got to be careful with. Okay, and now I'm looking at this whole thing is being divided by 25. So each term is really being divided by 25. And this simplifies to negative 3/5 I plus 2. In the second one, this is what it looks like when we set it up to multiply by the complex conjugate. Go ahead and multiply out your numerator and denominator and start again when you're ready. Okay, this is what I got when I multiplied everything out using distributive property over and over again. And here I started simplifying, combining like terms a little bit, and I put in my -1 for I squared. And here I simplified, combined like terms. Here I'm dividing each part by 20, and then here I just simplified each part. Lastly, we're going to look at powers of I. Again, keep in mind that I squared equals -1, but also let's keep in mind the power rule, that if we take a power to a power, so if I take a to the n to the m power, that's going to be multiplying your exponents together. So in our first one here, the first thing we want to do is rewrite this as I times an even power. And so what we really have here is I to the first times I to the 62nd. And when we're multiplying like this, then we would add those exponents together. So I'm going to get rid of that part. And now I can rewrite this as I times I squared, because I know what I squared is, to the 31st power. And here's the power to a power that's getting multiplied. And I keep rewriting this. I know that I squared is -1 to the 31st power. Now if I take -1 times itself 31 times, it's still going to be -1. And so this would all simplify to I times -1, which would be -I. Over here I have -6 times I to the 14th power. This is already an even number power, so I could just write it as I squared to the 7th power. 2 times 7 is 14, and I squared is -1. Now here again, if I take -1 times itself 7 times, it's still just going to be -1, and so I would end up with a +6 when I simplify. Now, if I do end up with -1 being raised to an even power like 8, then I know that that would be a +1. So that's how that would change that problem. Nice job challenging yourself and working through some of the most abstract material for the whole year. Keep it up. You're doing a great job.